Hi. Last week, we learned about the implicit function rule and how to use it in order to find comparative static derivatives in a market model and in the national income model. What we are going to do today is actually the extension of this rule. Because for now, we were assuming that we were dealing with just one function. However, what we've learned can be easily extended into a case where we have a set of simultaneous equations. Okay, so let's look at our set. So we've got n different functions, right, with n different endogenous variables. So, intact with what we said when we were learning matrix algebra, we've got n equations, n unknowns, so probably there's something we can do with it. However, each of these equations can have m exogenous variables, and m can be bigger than n, can be small, n can be smaller than m. However, it can be as big as we want. Because look, what we want to do now is that given these functions, we want to know if they define a set of implicit functions where all the endogenous variables can be expressed as functions of exogenous variables alone. Okay, and as it turns out, this is the case. So this system implies those functions under the conditions of extended implicit function rule. And again, we're just going to go through the rule to understand it when we can actually use it and what does it tell us. And as you will see, it will allow us to calculate comparative static derivatives of all endogenous variables. And as you will see now, when we turn back to ISLM and ISLMBP, they're gonna be way simpler. Okay, but let's go step by step. So, given the equation system 1, so the one that we have already discussed it. Now, if the functions f1, f2 up to fn all have continuous partial derivatives with respect to all x and y variables. Well, this is something we assume. So all the partial derivatives can be actually evaluated by us, and this is the assumption with which we start with every model. So let's assume that that it is fulfilled. In a similar, as you see, there's a similar condition we had in the first version of the implicit function. And now, second condition goes like this. At a point, 1, y0, y2, 0, yn, 0. So at a point, satisfying this system, the following Jacobian determinant is non-zero. Okay, and this is something new. Because now, except for, unlike in the case of the previous rule, we do not have one derivative, but we have determinant of the derivatives. Jacobian is a determinant of derivatives. Look, it actually works very similar to Hessian that we already discussed in detail during mathematics. Look, Hessian is a determinant of second derivatives, right? Jacobian is simply determinant of first derivatives. So look, how is it defined? Basically, what we need to do is to take all those functions that we've got over here from f f1 to fn and differentiate each of them by all endogenous variables from y1 to yn. And how do we do it? Look, just like in the case of Hessian, in the first row of the Jacobian, I'm simply differentiating function f1 with respect to y1, y2 until yn. Then, in the second line, I'm taking function f2 and differentiating it with respect to y1, y2, yn. And then I'm doing it like this until I'm at the last, in the last row, and I'm differentiating the last function with respect to all endogenous variables. Okay, so basically we need to just differentiate every function in each consecutive row by each endogenous variable in each consecutive column. And unlike Hessian, please remember, Jacobian might be symmetrical, but this is a special case. It doesn't need to be in principle. I hope you can see over here that differentiating function f1 with respect to variable y2 is different than differentiating function 2 with respect to variable 1. Right? Okay, now, assuming that we've calculated this Jacobian and it's different than 0, then there exists an n-dimensional neighborhood of point x1, 0, xn, 0, n, in which their variables from y1 to yn are all functions of the variables x1 until xn in the form of 2. So, in the following form. The implicit function satisfied. So, each of these values in this neighborhood, are identities. And look, so they also satisfy 1 for every n tuple from x1 to xm in the neighborhood n, thereby giving system 1 the status of a set of identities as far as this neighborhood is concerned. Remember, only in this particular neighborhood. Moreover, the implicit functions f1, f2 until fn are all continuous and all have continuous partial derivatives with respect to variables x. And look, the partial derivatives of y with respect to x are comparative static derivatives that we want to find. Okay, so look, let's imagine a case like this. Okay, let's just say that we are given this system of simultaneous equations. Now, we want to find now derivatives of all the y's with respect to all the x's. To do so, we're going to use extended implicit function. Okay, so what are the steps that are needed, that we need to take? First, we have this system. So, first thing I will do is to calculate the Jacobian of this system. So, what would I do? I would take each of these functions and differentiate each of them with respect to all endogenous variables. From y1 to y, I would calculate the determinant, and if this determinant happens to be different than 0, then we know that this system implies those functions. And let's just say that all those conditions are met. Of course, before we even can go to Jacobian, we are assuming that all those functions are continuous and have continuous partial derivatives. Okay, let's just say that this Jacobian is different than 0. What is going to happen next? Look, now with some very simple algebra, we can actually find a very simple way to calculate all the partial derivatives that we want. How do we do it? Look, first thing we would have to do is to calculate differentials of this system. So, I'm differentiating completely the first equation. So, here I will have partial derivative of f1 with respect to y1 times dy1 plus partial derivative of f1 with respect to y1 with respect to y2 times dy2. Then plus, we go on like this until we get to partial derivative of f1 with respect to y and dyn. But we know that this is not the only source of change, y. The second source of change are associated with variables x. So what do we have here? We've got plus fx df1 dx1 plus f1 dx2 plus and until df1 dx and dxm. Okay, and look, we know that y's are our endogenous variables, x's are our exogenous variables. So, good thing would be, of course, because this is all equal to 0, right? Because derivative of 0 doesn't matter with respect to what is always 0. And we can take those and put them on the other hand side of the equation, right? So I can subtract this, and I'm going to get the dyn equals to negative this. Okay, now look, we can do, knowing that, we can easily do the same thing for the second equation. We now differentiate second equation with respect to all the variables. First, all endogenous variables. And then exogenous variables, and we move them as well to the other hand side. So we will have here df2 dx1 dx1 plus df2 dx2 dx2 plus and df2 dxm dxm. Okay, we could do the same thing for every equation until we reach the last one. So equation n. And we also differentiate it first with respect to all the endogenous variables and then with respect to exogenous variables, which we, of course, all those derivatives we move to the other hand side. exactly the same thing for these equations, right? So the implicit functions. So what I'm going to do now is that I'm going to differentiate all the implicit functions. Okay, so we got a dy1, right, is equal to dy1 over dx1 dx1 plus dy2 dx2 d2 plus y plus dy1 dx and dx n. Right? And you know, by the same token, we can do it for y2. And we can do it like that until we arrive at the very last equation. So now we will have dxn equal to dy and dx. 1 here, 1 and here dx2, dx2. Okay, dx1 plus 1 and dx2 plus and dx and dx and I'm sorry. That was a little bit tight. And look, let's now notice one very simple thing. Look, those equations, so the differentials that we calculated over here are actually defining expressions like dy1, dy2 until dyn. And look, those same expressions are appearing over here, right? Look, you can see the dy1 is in every equation. We see that dy2 is in every equation, and we see the dyn is here in every equation. But if this is the case, then what we can do is to take those expressions and substitute them over here, right? However, there is one issue with that approach. And this issue actually concerns the feasibility of calculations. Look, if I would now substitute all of it, this expression would explode, it would be so big, and it would be actually really hard to get a useful information out of it. But let's remember why we actually started dealing with this. We started dealing with this because we wanted to find comparative static derivatives. And look, what comparative static derivatives we were interested in? Well, comparative static derivatives of this system. I want to know how x1 influences y1, y2 until yn, how x2 influences y1, y2 until yn, and so forth. However, if I would like to get this information all at once, it would be, as we said, very, very complicated. However, we can do it step by step. So look, let's just say that I want to know what happens to variables y1 to yn when x1 is changing the law. What can I assume? Look, let's say that dx1 is different than 0, which for us means x1 is changing, is increasing by some very, very small amount. We do not want the effects of this increase mixed with the effects of changes in values of any other x's. What do? We assume a second thing, that dx2 is equal to dx3, and all those are equal to each other right until dxm, and they are all equal to 0. Okay, and look, this thing actually allows us to get rid of a lot of stuff on the blackboard. And what we do, what we are looking at is the pure sole effect of x1 on all these variables, taking into consideration the interrelationships from all those functions without mixing it with the effect of any other variable. And look, what is this do here? First, we know that all dxm's are 0, which means that this part is gone. Right? dx4's the same, dx3's the same, dx2's are all gone. So look, we see the things that we were supposed to substitute into the system have gotten far, far simpler. Okay, let's go over here. As you can see here, we've got a very, very similar situation. All the exams are gone, so this part is gone. All dx2's, dx3's, dx4's, up till dx2's are equal to 0. So, as you see, this system, under this assumption, has been greatly simplified. Okay. Now that we know how that we see that it gotten a lot simpler, let's rewrite this system over here, and now let's just substitute into it the three differentials we've calculated previously. Okay, so we've got that df1 dy1 is times dy1 over dx1 dx1 now plus df2 df1 I'm sorry over dy1 dy1 dx2 dx2 and we go plus until df1 dy of course dy2 here we have dfn df1 dy n dx1 I'm sorry, of course everyone is x1 dx1 and it's equal to negative df1 dx1 dx1. Okay, and I hope you can see can see right away, now we've condensed this information coming from 1, 2, 3 to all n differentials into the first equation. Okay. Now, unfortunately, we need to do the same thing for all other equations. Okay. So f2 y1 dx1 plus f2 dy2 dy2 dx1 dx1. Now, plus, of course, df2 dyn 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 dx1 dx1 equals to negative f2 dx1 dx1. Okay, now the final equation goes as fn dy 1 dx1 dx1 plus derivative of second function with respect to y2, derivative with respect to x1 dx1, and and x1 dx1. Okay, I know that this system still looks a little bit complicated. However, let's remember what we said at the beginning. We assume that dx1 is different than 0 and dx2 until dxn are equal to 0. Okay, look, for now, the only information out of these two assumptions we utilized was the second one. We just got rid out of all changes in x's. However, we know something more. We know also that dx1 is different than 0. So what does it mean? If I'm 100% sure that dx1 is different than 0 because I assumed 0, I can divide both sides of this system of simultaneous equations by dx1. And look, each element here has got dx1. So now this is becoming far, far simpler. Okay, this is a good news, but maybe we've got some more good news. Look, we clearly see that some things are repeating. For example, in each equation, the first, we've got component dy dx1. Then, in each equation, we've got component dy2 dx1. And in each equation, we've got component dyn dx1. Look, if we've got such a repetition, this definitely looks like something we could put into a matrix notation. And look, this is exactly what we want to do over here. I want to take this system of simultaneous equations, of n simultaneous equations with n variables, and write it into matrix notation. Okay. So, if I'm going to do so, how is my system going to look? Well, okay, look, we see see, let's start with the first coefficient in first column. This is going to be df1, dy1. Then we would have df2, dy2. And we would have it like this until dfn, I'm sorry, dy1, dy1. Right? Then in the second column, we would have derivative of the first function with respect to second endogenous variable, derivative of the second function with respect to second endogenous variable, and derivative of nth function with respect to second endogenous variables. And of course, in the last column, we would have derivative of f1 with respect to yn, derivative of f2 with respect to yn, and derivative of fn with respect to yn. Okay, now let's see it further. What will be in the vector of endogenous terms? Well, there will be our derivatives. First would be derivative of y1 with respect to x1, derivative of y2 with respect to x2, until the derivative of yn with x1 with respect to x1. And finally, we would have a vector of exogenous terms, just the way it is over here. Okay, now look, as it turns out, what you see over here are all comparative static derivatives that we actually wanted to find. Right? They are over here. So, how can I find those? Well, let's just use the Cramer's rule. Like we did with numbers, we can do it the same with functions. How would we solve it? First, we would calculate the determinant of the matrix of coefficients. However, this matrix of coefficients is very specific. Look, in the first row, I have first function differentiated by every endogenous variable. In the second row, I have every function differentiated by every endogenous variable, and so forth. So as it turns out, in this particular case, our determinant is simply a Jacobian. So, as it turns out, we assumed that Jacobian is different than 0, but we will be checking it. But look, we are actually using something that we know. All we need to do is to calculate the determinant for this matrix, and we know we can find solutions. How do we find the solutions? Look, they are all here. If you want to find comparative static derivative of variable y I with respect to variable x1, what would we do? Look, we would say, of course, the Jacobian, we will be dividing by it. And then, look, if I want to calculate what is the partial derivative of, let's just say, y1 with respect to x1, what will I do? I will take the first column, I I'm going to take the vector of the exogenous terms. I'm going to replace the first column just like we did in case of matrix, in case of Cramer's rule, and I'm going to get this derivative. So look, generally, all I need to do is to calculate here Jacobian I with I equals 1, 2, right up till n. And those are comparative static derivatives that we were looking for. Okay, so look, now we understand the idea. The next thing we're going to do are, of course, applications. First, we're going to start with the market model, then we're going to move to ISLM model, and once this is done, we're going to move to ISLM BP. Okay, thank you for your attention, and see you in the next video.